Hello, we are starting a lesson on radicals and radical functions. All right, so here's just some basic rules is that if you're taking the square root of the number and there's no sign out in front, in other words, it's a positive radical or positive square root, then that's called the principal or the non-negative square root. If there is a negative on the outside, the negative, right, negative square root of a, then we'll have a negative answer for those that have the negative out front. The square root of 0 is 0, and if we're taking the square root of a negative number, it is not a real number. Now, we will talk about how to take the square root of a negative number in section 7.7, but it's an imaginary number, not real. Okay, so some of these are fairly basic. We're just going to take some square roots, and if you can do so without your calculator, that's a good idea to practice that some. And so if you take the square root of 400, it's going to be equal to 20, and that's because 20 squared equals 400. So to find the square root, we're looking for that number you multiply by itself to get that number that's under your square root symbol. And then on the next one, this is just the square root of a fraction. Now, you don't want to really enter this in your calculator. Some calculators would give you a decimal answer on this. And so you can write it as the square root of, I'm thinking ahead, the square root of 9 over the square root of 25. And then that would be 3/5. So you just take the square root of each number separately because the square root of 9 over 25 is the same as the square root of 9 over the square root of 25. And now the next one's a decimal number. You know the square root of 4 is 2, right? And so we have to figure out, you know, where does that decimal fit? This might be one you want to do with your calculator if you're not sure, but it would be 0.2. Now, if I multiply 0.2 times 0.2, I'm going to get 0.04 because remember you count the number of places after the decimal, and that's how many that you would put in your answer. All right. These problems are very short compared to some of the content that we've been working on not before this section. All right, so on this one we're going to look at this as the square root of 9, which is 3, and it will be negative because it's the negative square root of 9. And on the next one then we get into something a little bit different. So we've got a variable in here. So basically what we want to do is write this in such a way that we can take the root of that, and if it's an even number and we're taking the square root, then it is a perfect square and we'll be able to do that. Let me just give you a few examples here. Okay, so let's take the square root of x squared is x. Square root of x to the 4th is x squared, and that's because x squared times x squared is x to the 4th. Square root of x to the 6th is x to the 3rd. And so you can kind of start to see a pattern that if you divide the exponent by the index, and we don't usually write the index for a square root, but the index is 2, right? We're taking a square root. The other thing to look at is if I can write this to, let's see, let me write x to the 8th squared, and this goes back to those rules of exponents that if we have a power to a power, we're multiplying the exponents. So notice if I can get this 2 to match the index, which is a 2 on a square root, then my root will be x to the 8th power. So the shortcut is you can divide the exponent by your index. But you want to understand, you know, why am I doing this? So let's look at the 64 in the same way. If I wrote 64 as a power, I would have 8 squared, right? 8 to the 2nd power. and then this would be y to the 10th squared. And so because I have exponents of 2, which are the same as my index, my square root is going to be 8y to the 10th power. All right. So on these, we're going to use a calculator and then just round to 3 decimal places, which is the thousandths place. And it says check to see that each approximation is reasonable. Well, we know that if we're using a calculator, it's probably going to be reasonable, but something I would like to point out is if we're taking the square root of 11, it's going to be somewhere between the square root of 9 and the square root of 16, right? So it's between 3 and 4. So I know the square root of 11 is going to be 3 decimal point something. Even before I pull out a calculator to check this, I can tell right away that it's going to be between 3 and 4. And so even simple calculators often have a square root key because that's the most common root that we work with. So this one happens to be 317 when I round. It's actually 3.3166, so on and so on. And so it rounds to a 7. When I make this approximation symbol, the wavy equal sign is what I call it, then that's just showing that I did round this. So then if we look at the square root of 56, that's between the square root of 49. This is what I'm talking about. When you're checking to see if your approximation is reasonable, this can help, all right? So if I'm looking at the square root of 49, which is 7, and the square root of 64, and that's 8, so I know that the square root of 56 is between 7 and 8. So it's going to be 7 decimal, oh, let me put my wavy equal sign again. And in this case, it happens to be 7.483 when we round it to the thousandths place. And now 300 is not maybe one that is that familiar because those numbers are getting pretty big. In fact, a lot of times I'm not sure what that would be if I haven't worked with them for those for a while. But that there's a perfect square that is 289. And then that the square root of that is 17. And then 18 squared is 324. So the square root of 324 is 18. So the square root of 300 is 17 point, and this one rounds as 321. Okay. So that's just using your calculator. And then to check how reasonable it is, you would use that technique I was talking about. Okay, well, it's between these two numbers. And also, I'm just trying to help you understand square roots. Okay, cube roots. So when we take a cube root of a number, that means we're looking for a number that's to the third power that equals a. Okay, and so if we're looking at the cube root of -8, well, -8 is -2 to the third power, right? 8's 2 times 2 times 2, negative times a negative times a negative. And because this is an odd root, right? 3, 5, 7, those are odd roots. It's okay if there's a negative under the radical because it is a real number answer. So this answer is -2. And then you'll get more familiar with these as you work in this chapter. So the cube root of 27 is going to be 3, and the cube root of 64 is going to be 4 because 3 cubed is 27, 4 cubed is 64. And so we end up with an answer of 3/4. All right, so you'll get familiar too with the perfect cubes because as we work through these, you'll see more and more of these numbers. You can also make your own list and look at these perfect cube numbers. So basically we have 2 cubed is 8 and 3 cubes 27, 4 cubes 64, 5 cubed is 125. Those are some of the most common numbers that we'll be using when we're talking about cube roots. I think maybe I have a list on another lesson of some of those. And so look at this one. We're going to take the cube root. And so 125 is 5 to the third power. So negative 125 is negative 5 to the third power. This root is negative 5. On the next one, we're going to kind of use that same technique that we use for the square root. We want to write x to the third power in some way. So it would be x to the 5th cube, because 5 times 3 is 15. So basically I'm just splitting it in such a way that I can find the root, and that would be x to the 5th. So let's go back for a minute to that kind of definition of a cube root. If I take the cube root of a number, I get b. Then it means that b cubed was equal to whatever that number was. And so I've kind of been trying to show you that as we go. On this last one, we have the cube root of negative 64. So negative 4 to the third power equals negative 64. And x squared to the third power is x to the 6th. So my root will be negative 4x squared. All right, let's see how much time. Okay, so I'm going to stop this lesson and finish it, or I don't know how many videos it will take, 2 or 3. And I'm going to stop this one. This is the first one.